I'm Amanieu, and I'll be presenting Mambo X64, a low-overhead dynamic binary translator for ARM. So, first of all, some motivation. Consider a modern Android device. It comes with, nowadays they come with the 64-bit ARMv8 processors, which support both the 32-bit ARM instruction set and the 64-bit ARM instruction set. Now, unlike x86 64, which is a fairly straightforward extension of x86, the 64-bit ARM architecture was actually completely redesigned from scratch and is significantly different from the 32-bit ARM instruction set. Because of these differences, supporting both the 32-bit and 64-bit architecture in hardware actually comes at a cost in power, performance, area, and also in processor development time. So this has led to a desire to create 64-bit ARM processors which do not support the 32-bit instruction set in hardware. Now, there's a slight problem with that. It's that, while most Android applications are shipped as architecture-independent Java bytecode, in practice, many of them actually come with a set of native libraries, and typically these native libraries are only compiled for 32-bit ARM. So if all of a sudden your device can't run half of the apps on the App Store, nobody's going to buy your chip. So one solution to this is to use binary translation. So take the 32-bit code, translate it into equivalent 64-bit code, and just run that. And so that's essentially binary translation works by, as I said, reading sequences of 32-bit instructions and translating them into code fragments in the code cache, which contain 64-bit code. And as new code is discovered, new fragments are translated, and eventually all the code in the application has been translated, and execution just stays inside the code cache, going from one fragment to another. Now, there is one big issue of binary translation, is that it tends to introduce quite a bit of overhead. For example, Amanieu, which is a very well-known binary translator, introduces about, an application running under Amanieu is roughly an order of magnitude slower than if you were to run that application directly on hardware. Clearly, that's not acceptable for a general purpose solution. So the reason for this large overhead, well, there's several reasons. One of them is code expansion. So if you have an instruction in the source architecture, but don't have an equivalent instruction in the host architecture, which is the architecture that you're translating to, in that case, you're going to have to use multiple instructions to be able to precisely emulate the effects of the source instruction. Register pressure. Basically, the binary translator needs to hold a set of state, ideally in registers. This includes the whole register state of the source architecture, plus any additional state that the binary translator might need. And if you don't have enough registers, then you have to spill to memory and reload as needed. Branch translation and program counter access. The problem here is that the translated code fragments in the code cache are located at a different address than the source instructions. So whenever you have an instruction that refers to the program counter, you need to be able to recover in the translated code, be able to recover the address of that source instruction. This particularly applies to branches and specifically indirect branches, where you jump to an instruction, but the target of the branch isn't known at runtime and can vary from one run to another. In such cases, basically every time the instruction is executed, you have to do a mapping from the source target address to the address of a translated code fragment. Then there's system-level issues such as system call translation. The Linux ABI differs significantly between architectures, and this requires system call translation, especially any parameters for system calls that are in memory. For 32-bit ARM, all of those data structures have 32-bit pointers in them, but the host kernel expects data structures with 64-bit pointers, so you need to translate those. And finally, signal handling. So signals can occur at any point in the program, but when the translator receives such a signal, it needs to be able to send all the information about the signal to the signal handler of the translated application, and this includes the full register state at the point where the signal occurs. So to overcome these challenges, we developed Mambo x64, which is a dynamic binary translator, which translates from 32-bit ARM to 64-bit ARM. Now, Mambo x64 can run on any Linux system, including Android, and supports the full 32-bit ARM instruction set and thumb instruction set. And this includes support for tricky applications like JIT compilers and self-modifying code. Additionally, there's full support for signal handling, including recovering precise register state for faulting instructions, and it also guarantees that to deliver signals in a bounded amount of time, even if the program happens to be stuck in an infinite loop. Now, one of the key points about Mambo x64 is that it has very low overhead. It's very fast. So we evaluated Mambo x64 on 3 different ARMv8 processors. The Cortex-A53, which is a low-power in-order core, Cortex-A57, which is a high-performance out-of-order core, and the XGene-1, which is another high-performance out-of-order core. So in all of these experiments, we compiled the benchmarks as 32-bit ARM code and ran the same binary on the same processor, both natively and under Mambo x64. And as you can see, we have relatively low overheads on the Cortex cores, but what is particularly interesting is that on the XGene-1, we are on average 1% faster than native execution. So keep in mind that this is an average, and in practice, the different benchmarks vary from about 20% slower than native to 40% faster than native. Additionally, we show that Mambo x64 scales well to large numbers of threads, shown in the parsec benchmarks. As you can see, the average overhead stays stable at about 2%. At about 2% for up to 4 threads. For 8 threads, the overhead climbs up a bit, but this is actually due to one of the benchmarks finishing in just a handful of seconds, which starts to show the overhead of translation itself. Now, how do we actually manage to get such high performance? Well, we perform many optimizations. For example, we optimize we perform efficient translation of indirect branches, which has been a long-standing problem in binary translators. We implement several optimizations which we described in our TACO paper last year. The basic focus is to better exploit hardware branch prediction, including function return prediction. Then there's the usual compiler optimizations that you should all be familiar with, such as dead code elimination, constant inlining, and people optimizations. There's also, we also make use of dynamic register bindings. So for floating point registers, we can't actually fit all of the 32-bit floating point registers in the 64-bit floating point register bank, so we have to dynamically allocate them. And in this case, we have several optimizations, including the main one being keeping allocated registers live across fragment boundaries, so we don't need to store them to memory and reload them. And finally, we have two optimizations, which I think are the two most interesting, and I'm going to go into more detail about these two in this talk. These are speculative address generation and return-aware generation. For more detail about the other optimizations, have a look at the paper. So consider a normal load instruction. This is pretty simple. It basically says load a 32-bit value into R0 from address R1 plus R2. Now, a naive translation would be to translate it into this 64-bit instruction, which says load a 32-bit value into W0 from address X1 plus X2. Now, the problem here is that the address calculation here is done using a 64-bit addition. If this addition overflows, we will be accessing the wrong memory address. So this situation typically happens when you have a pointer and from which you access at a negative offset. Now, a correct translation would be to use a separate add instruction, which truncates the result to 32 bits, and then just load from the result using the result of the addition as the address, and this will work correctly. However, it is slow because it doubles the code size, it requires two instructions, and there's a data dependency between these two. So we really want to avoid this. So one thing that we can observe is that any overflowing load instructions, only load or store instruction, is going to access an address in the lower 20 gigabytes of the address space. The reason for this is that there is an optional shift by two places that's allowed by the addressing mode, which means that the first register has a range of 4 gigabytes, and the second register with the shift has a range of 16 gigabytes. So we note, so we have plenty of address space in the 64-bit process, so we can just reserve this the range of memory from 4 gigabytes to 20 gigabytes and trap any accesses to it. Then we can just use the simple translation, hope that it works. If it doesn't, we get a trap, and we can go back and rewrite the translated code to use the longer but correct form. Now, we also have a variant of this optimization which uses the sign extension feature in 64-bit ARM. See the paper for more details. Now, overall, this only improves performance by about 1% on SPEC, but on more pointer-heavy benchmarks, such as GCC, this actually has a significant impact with a performance improvement of over 10%. Now, let's talk about trace generation. So, trace generation, which is typically done using the next executing tail algorithm, is an optimization that works by essentially profiling the translated code using branch counters. And once a counter reaches a certain threshold, we're going, so a branch counter on G. Once the counter reaches a certain threshold, we will record an execution trace, so A, B, D, E, G, and once we reach back to our starting point, combine all of these basic blocks into a single code fragment. And then if we take a different path, then we can later on generate a second trace, C, F, G, etc. And the main advantage of this is that on ARM systems, the branch predictors are not that good, and we suffer from quite a bit of overheads from all the branch instructions between the different basic blocks, and these are eliminated in the traces. So we get better branch prediction, better cache locality, and generally more opportunities for optimizations within the same code fragment. Now, one of the features of trace compilation is that it automatically does function inlining. Now, this works great for dynamic languages, such as JavaScript, where this can be used to propagate type information across calls, but for binary translation, we actually don't get that much benefit from the inlining. And actually, this hurts us because it actually prevents us from taking advantage of hardware return address prediction mechanism. So take this example, which consists of a function, CDE, which contains a loop and which is called from two different places. So when we translate it with next executing tail, the inner loop will be turned into a trace first, because the branch counter on the backward branch in the loop will hit the threshold first. And after the function has been called a few times, a trace will be generated from outside. And this will effectively inline the call instruction here and inline the return instruction here. So far, so good. Now, the problem comes when the function is called from another place. So as before, you get the call instruction that's inlined. And however, when it comes to after exiting from the inner loop, it's going to jump to the existing trace starting at E. Now, the trace is going to notice that the return address isn't what it's expecting it to be. So it's going to have to do a side exit into a different block. So essentially a return misprediction. Now, this is where the performance impact comes from, because normally the hardware return address predictor knows where we were called from. It's pretty simple to keep track. There's a small stack in the processor that keeps track of all the past call instructions. However, in this case, we eliminated the call instructions, so we eliminated the call instructions here and here, so we don't actually have that information available. Now, we developed a variant of NET called return address trace generation, or just retrace. So, like before, the CD fragment is generated first. However, when the outer trace is generated, we do two things. First of all, we force the trace to end at the return instruction. So after E, we force the trace to stop and force a normal return. Secondly, when we do the trace starting in A, when we reach a call instruction, we actually pause the trace, execute the call, and once the call has returned, we resume building the trace. So this preserves the invariance of the hardware return address predictor, which is that the return target must be immediately after the call instruction. Therefore, when we translate the return at E, we can use a native return instruction, which takes advantage of the return address predictor. And the same thing happens for the trace XY. Now, using retrace instead of NET improves the performance of SPEC on average by 4%. But in some benchmarks, the improvement is up to 20%. Now, while these numbers may not seem very large, keep in mind that we are already very close to the performance of native execution, and we are essentially eliminating the last few bits of overhead of binary translation compared to native execution. So, in conclusion, I'd like to make 2 points. So, we developed Mambo x64, a low-overhead dynamic binary translator for Linux, which translates from 32-bit ARM to 64-bit ARM. And we're able to achieve faster than native performance through a wide range of optimizations. We have shown that binary translation can be competitive with hardware-level compatibility for supporting legacy instruction sets, and we hope that this may be the preferred way of supporting architecture transitions in the future. So, thank you. Any questions?
Nice talk. I have sort of the obvious unfair question. So now I'm giving up my fancy x86 machine. I'm moving to Alpha. So which lessons here generalize, and which lessons are more specific to this particular transition?
I would say that I haven't seen any binary translator using any of the two techniques I just presented. And I mean, speculative address generation really depends on whether the target platform supports 32-bit addressing modes or not. If it supports 32-bit addressing modes, then you don't need to do this. If it doesn't, then this helps a lot in performance. For return-wide trace generation, this should be pretty applicable. It sort of goes against the conventional knowledge that one of the main advantages of trace compilation is that it automatically inlines stuff for you, but we found that this is actually counterproductive. But yeah.
Hi, nice break. I just shout. You mentioned something about the poor quality of branch predictors on ARM processors. I would encourage you to frequently turn your knobs whenever a new generation comes out. Look at what's coming out from Qualcomm, Samsung, and Apple. There's some really good indirect branch predictors in the very latest parts. Just take a look at that. The second thing I would say is, so you were using SPEC and Parsec, is that what it was?
Yes, and Parsec.
So with benchmark suites that have very large instruction working sets, you might get different results, don't you think? SPEC and Parsec, they're kind of small instruction working sets compared to typical Android workloads.
Yes. And so at the time when this paper was written, these were the only benchmarks that I had tested on. Now I've done a bit more. I've got the translator working on an Android phone. It can translate complex applications like Angry Birds. I haven't been really focusing on performance lately. In the case of Android, it's more focus on making sure the applications don't take 2 minutes to start up while translating all of the code. And I've been, this is somewhat unrelated to this, but it's what I'm working on now is trying to combine it with some form of ahead of time translation to improve startup time and memory usage as well.
I was wondering if any hardware support in 64-bit architecture could have been provided to make this dynamic translation faster or easier. There's
no specific hardware support. unless you count like the 32-bit legacy mode as hardware support, but that's kind of cheating.
32-bit addressing, though, would have been hardware support, basically, right?
Sure, but as I showed, it's not actually necessary in this case. I think they added the load, acquire, store, release instructions to be compatible with the x86 strongly ordered memory model. I think, though it's unrelated to what I'm doing, but I'm pretty sure that's why they added it.
Any more questions? Oh.
Thank you for great talk. I was wonder how did you translate the program counter relative load store?
Sorry, the what?
So program counter relative load and store.
Sorry, I can't understand what's the question. PC relative loads. As I said, it's one of the. Actually, I have a bonus slide for this. You can see PC relative loads are actually just completely inlined into code cache as constants. Sorry, the PC relative loads are usually constants, and they are just inserted directly into the translated code.
Any other final questions? No? Then
This optimization really only works if the memory is read-only. If it's not read-only, then it goes through the slow path, which is to generate the address and then load from that. But code's usually read-only.
Okay, one final question here.
I was a little bit surprised that your like multi-threaded numbers were like lower than like the single-threaded case. Like, I was like wondering if like thread contention like does not like
can you
raise
speak clearer?
the overhead when you do the binary translation.
Sorry, I didn't get that.
So in your like graph that you had initially, comparing like with like multi-threaded.
This one?
Yeah, this one. So with like, maybe like I'm not like passing this graph properly, but like it seems as if like the, like for example with 4 threads, like it's like 2% overhead, right?
Yeah.
But like,
And it's this
it's
one.
like,
it's a different set of benchmarks. So
oh, okay, never mind.
so this one's parsec, this one's spec.
Okay, sorry.
As I said, actually the overheads of the different benchmark actually varies quite a lot. So this is on spec. You'll see that 100% compared to 100% line, it actually varies quite a lot and depends a lot on the underlying microarchitecture, the relative overhead compared to native.
All right, any further questions will be discussed offline. So let's thank the speaker again.